Yeah, come on everyone, let's start off. Great. So last thing that we did, we are discussing about this Newton's law of viscosity. And this is the formula that I gave you. F viscous is minus eta A dv by dz. Negative sign indicates opposition to velocity. A is the opposition to relative velocity. A is the area in contact. Eta is the quotient of viscosity. The eta is given in poise, but remember one SI unit is 10 poise, and others do keep your cams on. So let me just show you an example how this works. So this dv by dz is called velocity gradient, which is simply v2 minus v1 by z2 minus z1. So let me show you an example. So let's say we have a plank here. Let the area be some 2 meters square. Let the plank go with a velocity v is equal to 2 meters per second. And let's say eta is equal to some 60 poise. Let's say this depth is some 5 centimeters. And somewhere here, the speed of the liquid is going with half meter per second. And this height is 3 centimeters. So different layers have different things. We will talk about that. So this is your point one, and this is your point two. So the question is find the viscous force acting on this. So the viscous force will be backward. So first thing, when you do delta V by delta Z, and if you are going to use V2 minus V1 by Z2 minus Z1, remember this is valid only for thin layers. So here V2 minus V1 will be 2 minus half, and Z2 minus Z1 will be 5 minus 3 centimeters, so 10 power minus 2 meters. That is 3 by 4 into 100. That's around 75. Right, so just be careful there. For thick layers, dv by dz is not equal to v2 minus v1 by. How will you know? Generally, they'll mention the question it's a thin layer, so that is how you know it is thin. So then, if you try to apply the formula F viscous, the minus sign simply indicates the direction. So I'll just get the magnitude. Eta is 60 poise, so I should take 6. Eta A delta V by delta Z. So if you remember, this thing should be taken in SI units. Eta is 6. So this would be 6. Area is 2 meters square, and delta V by delta Z is 75. So that would be whatever 150 into 6. That's 900 newtons. The minus sign indicates it is opposite of the velocity, relative velocity. Clear with this? It's the direction, right? You can take it just like friction. Just like friction opposes relative motion between two surfaces, here friction opposes the relative motion between the two surfaces. So here, few things you have to take care. Is the example clear, everyone? So first thing, when you write F is equal to eta A dV by dz, be careful. Don't call this thing, F by A is not a pressure. Right? Because if you actually remember pressure का definition, pressure is force perpendicular to the area. So here, this F which you are acting is parallel. Getting it? So there's a name for this. We will learn in elasticity. It is called shearing force. So don't write that F by area is pressure. And second thing, this is a kind of an assumption. We assume velocity of the layer in contact with the solid. Contact with the solid surface has same velocity. That means if a plate is going at 2 meters per second, the layer which is touching that plate will also have the speed of 2 meters per second. Suppose if you look at the ground, the layer which is touching the ground will have the same speed as the ground. So if the ground is at rest, then the velocity layer which is at the bottommost layer also will be at rest. So let me show you how that works. So velocity profile. So if you ever see a river flowing, right, water in a river, the floor is at rest, so that will have zero velocity. As you go up, the speed increases, speed increases, speed increases. So the river is actually flowing faster and faster as you go up. So whenever a river is flowing, the topmost layers are going faster compared to the bottommost layers. So you must have noticed this, the river is flowing very rapidly, but you will see fish at the bottom, right? Fish, crab, all these small, small creatures, right? They're still walking at the bottom of the river as if nothing happened. But if you have a fish or something on the top, it will just get dragged away. So water in a river, this is how the velocity profile will look. Again, this need not be a straight line. It will be kind of a curve. So here the ground is at rest. So the layer which is touching the ground also will be at rest. So that is an assumption we are taking, which is, yeah, works most of the time. It's a reasonable explanation. Suppose if you take a water in a pipe, if you take a water in a cylindrical pipe, now look at this thing. The outermost sides will have velocity 0. So here the liquid, right, is like cylinders, coaxial cylinders. So this outermost layer will be at 0. As you go inside, this is how it would look. So the speed would increase, 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 and the speed is maximum at the center. Then again, speed decreases, decreases, and becomes 0. So at the center, the speed is maximum. And the shape is actually a parabola. We will prove this later on. We are neglecting gravity though. So did you ever see this thing, this Tom and Jerry, or in movies, right? That Tom, na, sometimes it takes a cigar, it smokes, and it releases rings like this. Ever seen that in a cartoon or something? So how does that work actually? Mhm. Let me show you how it looks. Yeah, you can get a box like this from Amazon. All you need to do is just seal the whole box, just make a circular hole. Then you fill it with smoke. Now you won't have a machine, so you can use agarbattis actually. You can take some 4 or 5 agarbattis, put them inside, and it'll be filled with smoke. Now look at the idea. Now if you hit the box, the gas inside will be pushed out of this hole. So that's why it's called a vortex scanner. Now think about the idea here. If the gas was actually ideal, when you hit it, you should have got a cylinder of gas, isn't it? But now because there's a viscosity, the edges will go slower and the center will go faster. So when you hit it, what will happen? The edges will slow down, the center will go away. So after some time, what you're left is a hole in the middle. What you get is a ring. You will see that in slow motion, say. Could you see the ring? So the edges are going slower and the center is going faster. So you will see that ring there. You can actually use this something like this, like yeah. So let me show you one more on this. Look at this thing. So even nature does something like this. Can you see those rings? So volcano is releasing smoke. You can see the rings in the air there. Or you must have seen somewhere here. A lot of the rings. There. Can you see that ring? That is what Tom used to do in the cartoon. Right? So this is physics. You make rings. And this is magic. You get a ship. We can't do this. You have to join some other classes. So there. Maybe we should join the Harry Potter school. Clear with this. So there, that's what I was saying. So it's called vortex cannon, yeah. So there. So you're getting the velocity profile here. So whenever the gas goes through a cylinder, the edges will slow down. So basically, whichever surface you're in contact, that will have the same velocity as that solid surface, right? So in case of a cylindrical pipe, the edges will be slowed down and the center will go faster. All clear with this? So there. So these are the two main assumptions there. Main assumption was this was the assumption there. So velocity of the layer in contact with the solid surface is same. And for thin layers, we can take delta V by delta Z as V2 minus Y, Z2 minus Z1. That's it. So technically, the only concept is this: F is eta A dV by dz. And we have Stokes' law. There are only two concepts, but let's see. We have some decent problems. Let's start with something easy. So let's say we have two surfaces. And let's say the space between them is filled with fluid. Viscosity is eta. Let the upper plate go with the speed of 3v and the bottom plate is going with the speed v. So this thing is going front and the bottom, both are not at rest, both the liquid layers are moving. And in the middle, you have this plate here, which is going with v by 2. So if I show you the top view, it would kind of look like this. This is going with 3v, this is going with v. Your plate is somewhere here, whose area is A. And you're going with the speed of v by 2, and someone is actually pulling you. You're not going on your own, someone is pulling this. And this distance from the top is d, and this distance from the bottom is 3d. So let's make it d by 3 and 2d by 3, better. And this same question, basically this is the, I'm just making it flat, so eta. So first question, find F external to maintain the speed of the sheet. Find F external to pull out the plate. So you're pulling the plate out of this. So how much force should you apply to maintain the speed of that plate? Second thing, where should the plate be placed so that F external is 0? So there is a particular place there. If you keep it there, it will go with V by 2 without applying any external force. And again, remember, there's only one formula that I wrote you. F is equal to eta A dV by dz. We're just going to play with that for today. Let's see how you handle this. Are you able to visualize the picture, how it is? So think of like, there are two bread pieces, and in the middle there is that, cheese ka slice, and you're pulling the slice out of the two bread pieces, something of that sort. Able to visualize now? Told you now, if you can explain it with something with food, you'll always understand. There. I hope the picture is clear. Anyone not clear with the picture, please ask me. I'll explain you again. But if you got it, go ahead. I'll give you a minute or two. Start with the free body diagram of the plate. And it's going with a constant speed v by 2. So how would you do the free body diagram? How many frictions will be there? There'll be two frictions. There is one friction because of the upper surface and this one friction because of the lower surface. You're getting it? See, because remember that what is that A? A is the area in contact. So this plate will have two areas, an upper area and a lower area. So when you draw the FBD, these are the forces here. So this is your F external. Can you tell me how will the friction be? Now, again, be careful. Huh? Friction ka job is not to oppose the velocity. Friction ka job is to oppose relative motion. Now ask yourself, who is going faster, 3v or v by 2? 3v is going faster, right? So I need to oppose that 3v and I have to support this v by 2. So this friction is actually acting forward. Is that making sense? Since the upper layer is going faster than this plate here, the friction is actually acting forward. It is helping that block to go forward. If this is v by 2 and this is v, both are going opposite. This friction is opposing this plate. Is this making sense? The frictions are not backward. F ka job is not to oppose your velocity, it is to oppose your relative velocity. So in friction, we have done this thing. Imagine if I had given you a question like this. There are three blocks, A, B, C. And let's say block A is going with 3V and this block is going with V by 2. And if this block is going with V. If I ask you draw the friction on A, B, C, how will you draw? So on A, you will draw the friction backward. On B, you will draw the friction forward, third law. And this friction will be F2 backward. And on C, friction will be F2 forward. Isn't that how you draw? So there is no difference in terms of the friction thing. The direction will be the same. Right? And then you're done. So you just calculate. So what is F1? So F1 will be eta area. So F1 is between 3v and v by 2. So relative velocity will be 3v minus v by 2 by distance between them is d by 3. That would be 5v by 2, 15 eta a v by d. F2 will be eta a, relative velocity is v by 2 minus of minus v by 2d by 3. That would be 3v by 2 into 3 by 2. That would be 9 eta a v by 4. So F external will be F2 minus F1. That would be 9 by 4 eta AV minus 15 eta AV by D. You will actually get a negative sign. The negative sign indicates that F external is not forward, it is actually acting backward. Is this clear, everyone? So if you solve this, how much will you end up with? I think I forgot a 2 here, no? There will be 2 there. Now, how much is this? Multiply 2 and 2, 30 minus 1. You end up with minus 21 by 4 eta A B by D. There. The minus sign indicates force is acting backward. Is this clear, everyone? You actually have to pull the plate backward, not forward. Right, Utsa? Right, Arya? Right, Samyak? What about the second part of the question? So where should I keep the plate so that the F external is 0? You want the plate to go with V by 2 without any external force. So indirectly, I'm saying F1 must be equal to F2. Get this? I'll give you a minute. So now what we do, let the distances be x and d minus x. You're saying F external is 0. Acceleration is 0. F1 must be equal to F2. So F1 will be eta A. Relative velocity is 3v minus v by 2 by x. This will be eta A. Relative velocity is v by 2 minus of minus v by d minus x. Eta A v will cancel off. This guy will be 5 by 2x. That would be 3 by 2 into d minus x. 10d minus 10x is equal to 6x. X is equal to 10 by 16, 5d by 8. Check. So it should be 5d by 8 from the top, right, Utsa? So if you can keep the plate there, then the plate need not have any external force. It will go with v by 2 without any external support. Is that making sense, everyone? So for every surface in contact, there will be one viscous force. Just like for every surface in contact with a solid surface, you have a friction. Any doubts on this? So how to get the direction of friction? Just assume similar to the blocks. And then how to get the value of friction? In case of a friction, it was mu into n, but here we have to use that eta A dv by dz stuff. All got this? Let's see one more. Shreyansh, clear with this? Shreyan? Clear? Aditi? Aditi, clear? Vedika? Got this? Now the next one. Let's say we have a long incline and almost infinity. On this long incline, we have a thin layer of fluid. Thickness is Z. Z is the thickness. And eta is the coefficient of viscosity. If I given variables, meaning it is an SI unit only. So if I given poise, then you be careful. On this, what you did, you kept a plate. Mass M, area A. Released from rest. So what will happen? The plate will start sliding on this thin layer because of the mg sine theta. Your gravity is present. First question, find velocity as function of time t. Find the velocity of the plate at time t. Plot vt graph, xt graph, at graph, av graph. Let's get the 4 graphs. Graphs are good ones. I hope you're able to visualize. This thing is sliding on the thin layer. Initially, you're starting from rest, and it's a long incline that will never reach the floor. It will just keep sliding forever. What is the velocity of this plate after time t? And then plot the four graphs: velocity time graph, position time graph, acceleration time graph, acceleration velocity graph. They would ask you VT and AT graphs. They're very common mains level questions. And whatever graphs I'm showing, again, they'll come later on in something called Stokes' law. Let's get the velocity as function of time t first, then we will see. Take a minute, get the FBD, get the equation. I'll give you a minute to get the equation. Then I'll show you that and I'll give you another 1 or 2 minutes to solve. Start with the FBD. There's nothing there. And again, don't think it's a viscosity chapter. The only new thing you learned, F is eta A dV by dz. Once you put that, it is laws of motion and kinematics. This is something you have to put it into your head. If you think every chapter is new, it will become overwhelming. You will start going crazy. Understand, every chapter is just giving you 1 or 2 things, and then you have to go back to your basics. Your basics are kinematics, NLM, friction, circular, work power energy, rotation, and collisions. That's your basic. No matter what chapter you do, something will fall into that category, except ray optics and semiconductors. So there are a few things, but yeah, most of them will fall. Let's see the free body diagram. After time t, let the velocity be v. So if you draw the plate, what are the forces? I'm just drawing the forces along the incline. Mg sine theta is dragging you down. Your viscous force is dragging you this way, and this is your acceleration and velocity. So this is mg sine theta. Again, remember the minus sign indicates it is backward. I already showed it in there. So is equal to ma. This is your F viscous. Just call it Fv. Now remember, it's a thin layer. It is given in the question. So mg sine theta minus eta a. So you're taking velocity between these 2 points basically. When you take the thin layer, this is the fluid between them. This point is going with v, so that layer is also going with v, and this point is going with 0, and the distance between them is z. So dv by dz will be v minus 0 by z minus 0, or v by z. Because it's thin layer, you can do that. So v by z is equal to mass into acceleration. Now you can write a is dv by dt and integrate. Try. Get this, I'll give you 2 minutes. Now it is all max from here. This much integration, you should have got used to it by now. You'll get a ln and an exponential. Can you see this thing? This is looking like a is equal to minus kv something. You know where you have done this? We have done this in calculus also. There. Remember a is equal to minus kv? This was the integration. So you end up with something similar. Get this. The physics part is done. Once you draw the FBD and got the equation, it is all max. Then if it is a mains level question, I would ask you this. Find the final velocity of the plank. That would be a mains question. Let's see. So I'll do it in the next page. Mg sine theta minus eta AB by Z is equal to mass into acceleration mdv by dt. So dv by dt will be g sine theta. So I'll just show you something here. You actually got something directly here. So A is equal to minus eta A by mz velocity plus g sine theta. So when you're drawing AV graph, this will be useful. Can you see? This is looking like y is equal to mx plus c. So AV graph is actually a straight line with a negative slope. Since we already did it, I'll just show you here. So if I draw AV graph here, so when velocity is 0, acceleration is g sine theta, and eventually, right, so this thing is just decreasing with a negative line. This is what would happen. So this is how the graph will look like. This point is called V terminal. We'll talk about that. So V terminal is your final velocity. So when A is equal to 0, meaning eventually mg sine theta becomes equal to the viscous force. That would be mg sine theta z by eta A. So this is the final velocity reached by the plate. So at this point, the viscous force and mg sine theta become balanced. Your speed will not increase further. So that's an AV graph. It's a straight line. But let's get this. So dv will be g sine theta minus eta A by mzv dv by g sine theta minus eta A by mzv plus g sine theta is equal to dt. Limits 0 to v, 0 to t. Now, if you actually notice this thing is looking like dx by ax plus b ka integral, which is 1 by a ln ax plus b. You can clearly see in the formula, a ka place mein we have minus eta a by mz and b ka place mein we have g sine theta. This much integration should be comfortable. So this guy would be 1 by a, which is eta a by mz ln ax plus b minus eta a v by. I could have taken them as p and q and I could have substituted them in the end, but okay. G sine theta limits are going from 0 to v is equal to t. Put v there, put 0 there, you end up with ln a minus ln b, which is minus eta a v by mz plus g sine theta by g sine theta. This would go that side. This would be. Did I miss a g somewhere? No. Minus mz t by eta a. So this would be eta v a mg sine theta. And like I said, it's all math at this point. This would be exponential e power minus mz by eta a t. Check it out if I missed something there. So from here you get velocity v is equal to mg sine theta by z eta a into 1 minus e power minus mz t by eta a. That's an exponential function. Play with this. So if you can clearly see here, this term here is your v terminal. Eventually at t infinity, you're going to get this velocity. When t tends to infinity, v terminal mg sine theta z by eta. Same thing. We got it from here also without doing this much calculations. So exam, if they just ask you v terminal, you just need to say the viscous force is equal to mg sine theta. So there's no need to do this much integration to get v terminal. So you can clearly see this will happen at infinity. That means when you leave it, you're not going to get this terminal velocity immediately. It will take a long time to reach this. Theoretically, never. So now how to plot the graph for this? But please have a look at the integration. it looks big. That's because there are too many variables. But I could have done something like, I could call this thing A, I could have called this B. Then in the end, I could have substituted A and B. It would have worked. Okay. You get used to it. Very common type of integration comes a lot. This level of integration should be very comfortable. Now, how to plot the graphs for this? So VT graph is easy. You can clearly see when time is zero, your velocity is zero. As time increases, velocity is increasing, but eventually you will reach a constant value. So you are getting closer and closer to this line, but you'll never reach that line. So this is your V terminal. That's your VT graph. How does AT graph look like? Now we can clearly see A depends on velocity, and if velocity is increasing, acceleration also will decrease. So you will start with g sine theta. This would be like this. You're tending to zero, but again, it'll take infinite time. Out of all, XT graph is a good one. So in XT graph, what is slope? In XT graph, the slope is velocity. What is happening to your velocity? Velocity is increasing, but eventually it will become constant. That means your graph here, there is a particular line here, theta, where tan theta is the slope basically, which is your V terminal. That means when you draw the XT graph, you start from zero. As you're increasing, eventually, right, you're getting closer and closer to this line, but you're never reaching this line. You're getting how is the graph? Because at infinity, your velocity becomes constant. A constant velocity in an XT graph is a straight line. So after a long time, you're going to become a straight line. So you'll get closer and closer to that line, but you'll never reach that line. That's how an XT graph looks like. Are the graphs clear, everyone? These are some pretty nice graphs. And we will see the exact same graphs later on. You will see similar equations. There, these are all the four main graphs. AV graph is a straight line. VT graph is an exponentially, increases and becomes constant. AT is exponentially decreasing. XT increases and becomes a line at infinity. All clear with this? Next one. Any doubts on this thing? Any doubts on the equations or the graphs? Please ask. I hope you can see that, right? Once you write the equation, it is math and it is just solving, and graphs is kinematics ka stuff. Third one. We have a disk, mass m, radius r, rotating with omega naught. You took this disk and you placed it on a thin layer of fluid. Thickness is z and viscosity is eta. Initially, the disk is rotating with omega naught. Now, if you take this and place it on this rotating liquid, now because of viscous force, it will start slowing down. A rotating disk is placed on a thin layer of fluid. Find angular velocity after time t. Initial angular velocity is omega naught. And you have seen this question like this before. Remember anyone where you've seen this? याद है question? A rotating disk is placed on a rough surface as shown like a dosa on a pan. Find the time when it stops rotating. So there, it was the friction on the ground which was stopping you. Here it is a viscous force which is going to stop you. So this is what I was saying. Questions will not be new. You must have seen them somewhere, but few variations. Now the element and everything will look exactly same. Only thing there, friction was mu into n. Here, friction will be eta a dv by dz. Let's see how will you handle this. So you took a rotating disc and there's a liquid and you kept it. Yeah.
Sir, we need to assume that the disk is never going like at the bottom, right?
Sinking का बात कर रहे हो? I assume it is not
हाँ,
sinking and all that
okay.
will. Yeah. Anyone not clear with the picture? Ask me. Think. How will you choose an element? You already know how to choose an element. You take a thin ring at a distance x, dx thickness, and use the formula eta a dv by dz. V is what? V is the velocity between the layer and the ground. Try. Everyone should try. Take 2-3 minutes. It's completely fine if you don't get anything, but put some fight. That's what actually helps you. So you should try and get some water and calm. So how do we get this? Near सम्यक. You'll you'll not get a constant acceleration. Exponential आएगा इसमें भी. Somewhere you assumed alpha is constant, क्या? And it's easy to feel that also. Think about this. The slower you go, lesser the velocity. Lesser the velocity, less the frictional force, isn't it? Means as you're slowing down, the friction is also decreasing continuously. So you won't have same alpha. So that much is clear. This is a decay function. The function is killing itself. The slower you go, the lesser the friction. Lesser the friction, lesser alpha. Lesser alpha means you'll even slow down even much less. So this, technically speaking, should must not be stopping that easily. So how do you choose an element? Again, let's see. I'm showing you the top view or the bottom view. So we choose an element at a distance x. It's exactly the element and everything are exactly same what we did in rotation. This is what I'm saying, when you remember certain models and all, right? You can directly use that part of the thing in some other chapter in a different way. And technically speaking, that is how actually you learn anything. Let's say tomorrow you're into architecture. What do you think they'll make you do? They will take up some, the top 30 or 40 buildings, and they will tell you, study each and every design, why it is constructed that way. And this way, technically, 40 models, you are, remembering everything. And what is the idea there? Tomorrow, when you go to a design and you face a problem, then you have something to go back and say, okay, in the 22nd model, they had the same problem with the tower in this problem. So I can take the solution from here. And here the roof ka problem is exactly same like the 14th building ka problem. So you take up the solutions from different buildings ka thing, and then you try to maybe modify a bit and try to adjust it. Learning, when you're solving physics, it is no different. You are acquiring different skills, so you are need to learn different models. So when you see a question, your brain will figure out, oh, this thing is looking like that, so let me use that. So, and if this guy is rotating with omega, how will the friction be? Friction will be tangentially backward. If you see, all the story is exactly same. Now, if you look at the side view, this ring which you have taken here, so this point will have a speed of x omega. And this thing, when you place it on a floor, the speed of this point is v is 0. So remember, when you do dv by dz, because it's a thin layer, you're taking the velocity between this ring and the floor, so which is x omega minus 0 by z. That's your dv by dz. Now, what is the viscous force on the ring? The tangential direction. What is the formula? Eta. Area will be 2 pi x dx, dv by dz, which is x omega by z. So eta area dv by dz. This is the tangential force acting on the ring. So what is the torque on the ring? Torque on one ring is your radius x into the viscous force on the ring, which will be 2 pi eta omega by z xx x cube dx. What is the torque on the disk? Integrate 0 to r torque on the ring. So when you integrate this, you end up with 2 pi eta omega by z. That would be r power 4 by 4. Now, be careful. When you're integrating here, you're integrating with x. So omega is constant. So you're finding the torque on the disk for a given omega. That would be pi eta omega r power 4 by 2z. And look at the torque here. It is not constant. Torque is changing with omega. The slower the disk, lesser the torque. Please have a look at this thing. So you have to take a ring, because every ring has a different speed. Then every ring has different area, every ring has a different speed. So the viscous force on each ring is different. Then when you want to find torque, you have to multiply with x. So that is also different. So you're actually getting an x cube function here. That means if I had asked you a question like this, the ring on the outermost one and the ring at r by 2, the outermost one is experiencing almost 8 times more torque. So once you got this, you're kind of done. So torque on the disk is pi eta omega r power 4 by 2z is equal to omega. We know torque is equal to I alpha. I is nothing but mr square by 2, and alpha is nothing but minus d omega by dt, because you're decelerating. Omega and alpha will be in the opposite direction. R square goes off, 2 goes off, you end up with the d omega by omega is equal to minus pi eta r square by mz dt. Integrate on both sides. This will go from 0 to time, and this will go from omega naught to omega. This will be ln omega by omega naught minus eta r square time by mz. We get omega is equal to omega naught e power minus eta r square by mz into time. So basically, this thing will never stop. This will take infinite time to stop. Hmm. Right also. You just got a, we didn't get a minus sign. Are you clear with the steps? So there are two integrations everyone here. The first integration is with respect to x. The second integration is with respect to time and omega. So you have to integrate two times. Please have a look at the steps. Hmm. Minus sign is missing, right? Arya. Your omega is increasing. You created a free energy source. So basically यहाँ पे minus miss कर लिया तूने because alpha omega are opposite, it will be decelerating.
My bad.
Now see, that is, I'll tell you one thing. Generally, right, physics में 99% of the time, at least 11th and 12th physics, you will, one or two places are there, but rarely you will get e power plus something. I told you this before also. And but वहीं पे एक जगह था ना, tension is equal to mu power theta. The tension in the string. You said this thing, said this is plus. याद आया तुझे? So, but maximum times, right, you'll always get a minus sign. And simple logic is this. If you had got a plus sign, that means your time increases, you'll go to infinity. If you go to infinity, means you have infinite energy. In real life, infinite systems, you can't get infinite energy. All clear
Yeah,
with the equations,
makes
everyone?
sense. So you meant the pulley wala problem, na? Rough pulley.
Ah, there it was saying it is impossible to pull. Uska infinity ka meaning wo tha. But generally, when you get omegas and velocities and accelerations and stuff, you can, velocities and omegas general, they'll never go to infinity. All clear with the steps, everyone? Now, this question, right, you can play around like this also. What if they give a box? If you see a vehicle, right, they have something called a gearbox. So it would be like this. So you have a gearbox here, and maybe someone kept a disc like this. And now it is rotating. So this thing is filled with fluid on both the sides. So the only difference will be the area will be double, isn't it? There is one friction on the top, there's one friction at the bottom. So this thing is simply like that. When you can make questions like this, you can make a cone kind of thing. Inside this cone, you kept a solid thing like this. This is given omega, and this space between them is filled with fluid. Right? And so here, what would happen? This point, if you take at a distance x, so this will go with x omega, and this would be the thickness z. So you can play around like this. So the idea is always the same. You have to get that area, get the torque on each ring, and then you can integrate. Clear with this? Next one. This would be a good question. Plus, this is also the derivation for something called Paul's equation. So we have a cylinder. So this is a part of a cylindrical pipe. So liquid is flowing in a pipe, and you have taken a part of it. So here the pressure is P1, here the pressure is P2. The radius of the pipe is R and the length is L. So this is the liquid is flowing with some velocity, viscosity is eta. This is a distance x from the center. The flow is steady flow. It's not a turbulent flow. Matlab every section is just going with a given speed. Different sections can have different speed, but they're maintaining the speed. So here P1 minus P2, we'll call it delta P. This is the difference in pressure across the pipe. So because of this extra pressure, the liquid is being pushed through it because there's a viscosity. So first question, find velocity of the layer at a distance x from the center. This would be a good advanced paragraph. Find the volume flowing per second through the pipe. How much liquid is flowing through this pipe every second? Find the velocity gradient dv by dx. Now remember, this is not a thin layer, so you can't use that formula. dv by dz is not equal to v2 minus v1 by z2 minus z1. Let's see how you do this. Let's get this. And I gave you a little idea already here. If you remember this velocity profile, this is how it flows. Look at this thing. So every layer will have different speed, but the speed of layer is constant. I hope you're getting the meaning of that. No one is accelerating here, but everyone is going with different speed. The guy in the middle is going much faster. The guy here is going a little slower. Here is going slower. Here it is going slower. But they're going with that same speeds. Everyone maintains their velocity. So none of the particles are accelerating, but all will not have same speed. Think, how will you handle this? Hope the question was clear. So we have a pipeline, inside the liquid is flowing. So we took a part of the pipeline. Across the pipeline, the pressure difference is P1 minus P2, length is L, radius is R, liquid ka viscosity is eta. What is the speed? Nothing is mentioned. One thing I know. The speed of the liquid on the edges will be zero. That much we know. What is the velocity of the liquid layer at a distance x from the axis? And how much liquid is flowing through the pipe every second? And what is the velocity gradient? How do we approach this? Do one thing. Take a cylinder of radius x and try to draw the FBD. Take a cylinder in the middle like this. This cylinder. Try to draw the FBD of this. Find all the forces acting on this and see what you will get. Let's start from there. Let's see if you can get some ideas there. Let's see the free body diagram. So what do you mean by steady state here? So each layer here has a constant velocity. Right? The layers can have is different. So velocity of the layers is different, but they're not changing with time. So we can say acceleration of each layer is 0. So if acceleration of each layer is 0, then this acceleration of the cylinder is also 0. That means from the left-hand side, the pressure is pushing P1 pi x square. From this side, it is pushing P2 pi x square. So this difference in pressure must be acting on this surface here. The friction is like this, F viscous. Are you guys able to visualize how it is? Look into my screen. So if this pen which I'm holding in my hand is the cylinder, so if I catch this thing like this, and if I try to pull the pen out, can you tell me how will the friction be on the pen? It will be on the surface, isn't it? Are you able to visualize? It's like a cylinder inside here, and if I'm trying to just pull it out, how will the friction act on this pen? It will act on the surface of the cylinder. Are you able to visualize that? So the viscous force is not acting inside or anything, it is acting on the surface. Whereas the pressure is acting on the cross-sectional areas. Is that clear, everyone? So the viscous force will act on the surface, whereas the pressure will act on the. So F viscous will act on the surface area. Since the acceleration is 0, P1 minus P2 into pi x square, that's your force, must be equal to F viscous. Remember, this is x and the length was L. And what is F viscous? So this is delta P pi x square is equal to eta, the surface area, which is 2 pi x into L into dV by dx. So this is the surface area of the cylinder. That's where the friction is acting. Viscous force is acting. Uh, Wait, this thing now, it should be P2 minus P1 because we generally take final minus initial. Because delta P is P final minus P initial. So there actually we got the velocity gradient directly from here. dV by dx is equal to pi pi will cancel minus delta P by 2 eta Lx. That's your velocity gradient. Then you can just integrate this. dV is equal to minus delta P by 2 eta L x dx. Integrate on both sides. Now be careful here. At the circumference, velocity is 0. V is equal to 0 at circumference. So your limits when x is equal to r, your velocity is 0. So the general habit, right? We think 0 to v and 0 to x. That is wrong. Clear? Because at this thing. So when you integrate this, you end up with v is equal to minus delta p 2 eta L x square by 2. Limits will go from x to r. So get v is equal to delta p by 4 eta L r square minus x square. Check. That's your velocity. Yeah.
Sir, I think like the logic which you said for putting the minus sign, I feel that is kind of incorrect.
Yeah.
Sir, I
When you
think
say dp is what?
uh, so the pressure difference due to the
Normally, whenever you
viscous.
write x, कैसा लिखते हैं हम? This thing I taught you here only. Do you remember? Mathematically, we always assume the function is increasing.
Okay, ठीक है.
So
No, sir,
mathematically,
like
we'll always assume it is an increasing function. So here also we'll assume p is increasing. But if p is increasing, then p1 should be greater than p2, na?
okay, हाँ, right. No, like I was thinking कि x is मतलब dz is minus dx, so that's why it's minus.
ठीक है मतलब x how are you taking depends on like you're taking from the surface बोल रहे हो.
हाँ, अगर हमने सरफेस से हम वेलोसिटी का डिफाइन करेंगे ना प्रोफाइल, तो फिर माइनस
ठीक
डी
है.
एक्स होना चाहिए.
Maybe if you are convinced with that, you're comfortable, it is fine. But generally, we always think, right? We take functions are increasing.
Yes, sir. I get it.
So there, we got the velocity here. So v is equal to delta p. This is a pretty good advanced paragraph question, right? R square minus x square. So when you take x is equal to 0, you get the maximum speed. So this is the maximum speed the liquid is going at the center. Delta p r square by 4 eta l. So there are a lot of things I can ask you. Please have a look at this. Clear what we did? We just drew one FBD and then we got it from there. Take a break. After the break, we'll continue from here. Take a 5 minute break. We still have to find how much liquid is flowing out every second. Any doubt so far? Chalo, come back in 5 minutes then. Yeah, yeah. Okay. Okay. और आइमा तो लास्ट ईयर वहीं पे ज्वाइन किया ना, वो कहाँ पे ज्वाइन किया, बिट्स में? ओह, ये मीटे गए हैं एक बार, आया था मिलने के लिए. हाँ, okay. क्या आके क्या बात करना है अभी? Yeah. नहीं, उस टाइम भी भाई आया था, यही बात किया था, मैंने वही बोला था, बहुत अफसोस किया आज अभी आके क्या बात करें, सेम रिपीटेशन नहीं है. ये यार, इनको काउंसलर चाहिए तो बाहर किसी को हायर करना है ना, इनको क्यों यूज कर रहे हो? अब इससे नेक्स्ट कुछ डिस्कस करते हैं, बोलो ना, फोन कॉल में कर लेते हैं. अब बोल देना सर, बच्चों का मेन एग्जाम चल रहा है, इधर दीदी ऐसा ही बोल रहा है, मेन एग्जाम में छोड़. हाँ, वो तो उसको एडमिशन लेना भी नहीं है, सिर्फ आके बात करना है ना. बोल देना, बाद में देखते हैं. वीक तो चांस ही नहीं है, वीक तो सिर्फ थर्सडे ऑलरेडी हम 10:30 को बुला रहे हैं ना कोई पे. हाँ, तो मिलना ही है मुझे, तो ये बच्चों को बहुत डाउट होते हैं, डाउट छोड़ के इन लोग के कौन पीछे होगा. तो बोल देना सर, मेंस चल रहे हैं अभी, मेंस के बाद सर मिलूंगा अभी. वो बेस्ट है, अभी उसका अभी तक नहीं, तो अगर अर्जेंट है तो फोन कॉल पे कनेक्ट कर सकता हूँ, मिलना है तो मतलब यहाँ पे वेट मेंस के चलो. उसको अगर लेना ही है, वो अलग होता था बस. मुझे नहीं लग रहा वो लेगा, बिकॉज लास्ट टाइम ऑलरेडी स्पेंड किया ना, कितना बर्बाद करेंगे. हाँ, बाहर गया था ऑलमोस्ट, आई थिंक 20-25 मिनट्स बाहर गया था वो. इतना ये नहीं हो गया, यही स्टोरी है. पता नहीं आपसे क्यों डिस्कस नहीं करते, इन लोगों को क्या लगता है, मतलब बच्चे का कंफ्यूजन है, हम क्या कर सकते हैं यार. तो उसके बाद बिल्कुल. ठीक है, चलो. वही है ना. ओके. ठीक है. किसके लिए? नेक्स्ट ट्यूजडे होंगे एकदम. विक्रांत सर है सैटरडे को मिलना है तो. तो देन नेक्स्ट ट्यूजडे होंगे. नेक्स्ट. हाँ, तो नेक्स्ट ट्यूजडे, नेक्स्ट थर्सडे, नेक्स्ट सैटरडे आइदर आ जाओ. चलेगा. और इन दिनों को इन्फॉर्म कर लिया क्या ये बीपी वाले को? डेटा का पॉइंट ही नहीं है। ठीक है। और कुछ का बात ही नहीं है, देखा वाइफाई नहीं है तो कोई हिल ही नहीं क्लास में बैठ के। ठीक है, चलेगा। हाँ, कर लो बाद में तो। Sure, let's start off. So, flow would be at one. Right, Utsa? We'll get something like that. So, we need to find the total liquid flowing per second. So, how to do that? So, once you got the velocity here, so at a distance x, if you take a thin cylinder here of radius x and dx, so liquid is coming out of this. And we studied in fluid mechanics, remember volume flow per second? Volume per second through the thin cross section is area into velocity. A into V. If you remember equation of continuity, maybe we did this thing. Area into velocity will give you the volume flow per second. So what is the area here? Area will be 2 pi x into dx. That is the area of the thin cross section, and velocity is this guy. which is delta P by 4 eta L R square minus X square. So this much liquid is flowing through this thin pipe. So if you want the total liquid flowing through the pipe, we have to integrate all this volume flow. That would be delta by 2 pi by 2 eta L integral R square x dx minus x cube dx from 0 to R. I know the result, so I'll write it down. So you'll get delta P into pi R power 4 by 8 eta L. So that would be R square by 2, and that will be R power 4 by 4. So this much liquid flows every second. So have a look at this. I'll put on this formula in the next page, and others do keep your cams on. So that quite an important formula. Definitely remember this. The volume per second through the pipe is given by delta P pi R power 4 by 8 eta L. R is the radius of the pipe. Delta P is the difference in pressure. So if you notice that, that means if you take a pipe of radius R and 2R, that 2R will take 16 times more liquid will flow per second. L is length of the pipe, so longer the pipe, the more difficult for the liquid to flow. Eta is your coefficient of viscosity. So this equation is called as Poiseuille's equation. You should definitely remember this formula there. There is a question like this in units and in errors. In Poiseuille's equation, which quantity has to be measured carefully to decrease the error? Radius, because it is power 4. This is the proof of the Poiseuille's equation. So this itself will be an advanced paragraph question. That result is also important. Any doubts on this integration, please ask. So area into velocity will give you the volume flow. But every point has different velocity. So what we do, we take such a thin cross section dx. We can assume velocity is constant in the dx, and then we do a into v, and then integrate the whole stuff. Clear with this? Now we do something good. So this will, next thing what we are doing, right? We are going to compare this with your Ohm's law. And this, we are going to do this, in 2 more chapters. We're going to do this in heat transfer also. So listen to this concept. The thing is, Max does not care if we have two identical mathematical equations. And if you just change the variables, Max does not understand the difference between them. That means if you take your Poiseuille's equation, which is volume per second, which is delta P pi R power 4, I'll just take small r by 8 eta L. You can rearrange this equation a bit. So volume per second becomes delta P by 8 eta L by pi R power 4. Now, if you look at this equation will give you kind of, it looks like I is equal to delta V by R. I is your current flow. Here it is a volume flow. Delta V is your potential difference. Here it is your pressure difference. This is the resistance. So this bottom is behaving like resistance to flow. Mathematically, they look identical. That means we can define something now, resistance R This is how actually you study water flow circuits. Let's say you're supplying water to an entire building or an area. This is how you can treat them like resistors, and you can solve the whole thing. So resistance to the flow is given by 8 eta L by pi small r power 4. In case of resistor, the formula was rho L by area, but okay. But if you see the remaining things, right, here it is a liquid flowing per second, here the charge flowing per second, potential pressure difference, potential difference. So the denominator term is looking like resistance. So what do you mean by that? So whenever someone asks you to solve, let's say there is a bunch of water connections and water pipes and all, and you want to study how the water is flowing. So if you have a pipe of radius small r, length L, you can replace this with a resistor, right, which is equal to 8 eta L by pi r power 4. And then literally you can do everything that you did in circuits. So if you have two pipes in series, when you say they're in series, if they have same volume per second, when you have same current, so here current is similar to liquid flowing per second. So let's say someone connects two pipes like this, R1, R2, L2, and L1. So you can replace them with two resistors. R1 will be 8 eta L1 by R1 power 4, and R2 will be 8 eta L2 by pi R2 power 4. And then you can say R equivalent is equal to R1 plus R2. And if someone asks you how much liquid is flowing per second, then you will say volume flowing per second is simply pressure difference by R equivalent. Just like how do you find the current? Potential difference by resistance, equivalent resistance. Everything that you learned in current electricity in school works. Simply replace R with 8 eta L pi R power 4, replace the pipe with the resistor, series, parallel, everything that works. These are water circuits. Is that making sense, everyone? Because Max does not care what is P and what is V. Max will simply say you called V as P. Max does not understand the difference between change in pressure and change in potential difference. For Max, it is simply two different variables. So mathematically, as long as the functions look same, you can use the results. All clear with this? I think you should note down this stuff. Huh? You should know this formula and note down this stuff. Note it down, just keep it to the side in case you don't remember. So when you see a pipe, you can replace with 8 eta L pi r power 4. So that is series. How does parallel look like? So when you say two resistors are in parallel, if they have same potential difference, so here they should have same pressure difference. So potential becomes pressure, current becomes volume flow. So if you connect two pipes across the same pressure difference, P1, P1, P2, and P2, we say they are in parallel. R1, R2. So 1 by R equivalent is 1 by R1 plus 1 by R2. R equivalent will be R1, R2 by R1 plus R2. Now, there is something also called as Wheatstone bridge. We will see this in more detail, but I'll give you the idea for now. Take it, and later we will see this in current electricity. So if you have resistors like this, R1, R2, R3, and R4, and this is R5. if R1 by R2, that ratio becomes equal to R3 by R4, you can actually kind of guess it out. In this point, ask yourself. In school, you studied now, if you have two resistors in series, R1 and R2, the potential will divide in what ratio? V1 and V2 will divide in the ratio of R1 is to R2. Agreed? Because current is same, na? V1 is equal to IR1, V2 is equal to IR2. Similarly, if you have two more resistors, R3 and R4, and let's say then if this difference is V3 and V4, and V3 by V4 will be also R3 by R4. Agreed? Now, if R1 by R2 becomes equal to R3 by R4, then V1 by V2 becomes equal to V3 by V4. That means any point here A and any point B here, they will become equal. That means VA becomes equal to VB. Does it make sense? Because if this potential and this potential ratio, this potential and this potential ratio is same, and this whole chunk is connected like this to the parallel, that means A and B must be same potential. If VA and VB are equal, if you keep any resistor between them, what will happen? Current will not flow through it, isn't it? Because there is no potential difference. Is that logic making sense? If VA becomes equal to BB, then any resistor between A and B, there will be no current. Then there will be no current. Right, in a resistor between A and B. So if you connect a resistor between A and B, you can just remove it. So basically that's your bits on bridge. If R1 by R2 is R2 by R4, then R5 can be removed. Remember this? You're going to see this in 3 more chapters. So it has to maintain this ratio. So R1 by R2 must be R3 by R4. Then your circuit becomes like this. This is easy to solve, isn't it? The top two are in series, and they're in parallel. This is called Wheatstone bridge. There, series, parallel, Wheatstone bridge. All clear with this. So you can just simply replace the pipes here with resistors and solve all this stuff. Let's see a question. Let's see a question. So we have a big pipe here. We have a small pipe here. Let the radius be 2a. Let the radius be a. Let the length be L. Let the length be L. Viscosity is eta. Here the pressure is 2p naught, and here the pressure is p naught. This thing here is your interface. So that is where both the pipes are joined. First thing, find R equivalent resistance. Find the volume flowing per second, how much liquid flows through the system, and find the pressure at the interface. So find the equivalent resistance for the fluid flow, find how much liquid is flowing per second, and find the pressure at the interface. Let's see. Okay. See, first thing, let's just replace them with resistors. See, once you make it a resistor, it becomes easy to solve. So let this resistor be R1, which is 8 eta L by pi R power 4. That is pi A 2 power 4. So for convenience, I'll call this R. Then R2 will be 8 eta L by pi A power 4. So if this is R, then this must be 16R. Agreed? Because that is 1 by 16. So what is R equivalent? R1 plus R2? You can write this thing as 17R. There. Then what is the current? Current here is nothing but the volume flow per second. Volume flow per second is nothing but the pressure difference by R equivalent. The pressure difference here is 2 P naught minus P naught by 17R. P naught by 17R. Right? And how do you find the pressure difference? Look at this thing. Huh? Here the pressure is 2 P naught. Here the pressure is P naught, and the center let the pressure be X. And let the current be I. Because they both are in series, we'll have same current. So this is a pretty good technique. We are going to use this multiple times later on. So what is the current in the circuit? So current in the resistor here is the potential difference across the resistor by resistance. Do you agree with that statement? Potential difference across the resistor, which is 2P naught, minus X by resistance, which is R. Current in this resistor, second resistor, is potential difference across the resistor, which is X minus P naught by resistance, 16R. Please have a look at that equation there. Because for each resistor, the current is the potential difference across that particular resistor by its own resistance will give you the current. Since both are series, the current must be same. RR will cancel. This will be 32 P naught minus 16X is equal to X minus P naught. You end up with X is equal to 33 P naught by 17. So if you just want to find X, you need not put any effort there. You'll actually get it pretty easily. That R will cancel off. You're only interested in the ratio. Have a look at this. All got this? Clear how we did this thing. Once you convert everything into resistor, let's call it R, and this will be 16R because pi A power 4, no? So if your radius doubles, it will become 16 times. So 1 by 16. All got this? Trishi, clear with this? Pratyasha? So can you tell me what will be the answer for this? Just let's say if you have two pipes like this, let's say this is 3P naught, and let's say this is P naught, and let's say this is 3A, and this is A. Can you find the pressure at the interface? Get this fast, I'll give you a minute. I just changed the numbers. It is the exact same question. I just changed the numbers. So pressure is 3P naught and P naught. Radius is 3A and A. Find the pressure at the interface. Get this? So how do we start? Let this be a resistor. Let this be a resistor. So let this be R1, which is 8 eta L, same length, pi 3a power 4. If I call this R, then R2 will be 8 eta L pi a power 4. That is 3 power 4. So this is 81 R. That's a big resistance. So if this is 3p naught and this is X and this is p naught, the current is same. So I will be current in the first resistor is 3p naught minus X, that is the potential difference, by resistance R must be equal to the current in the second resistor, which is X minus p naught by 81 R. You can solve this, you'll get the answer. Are you clear with this? How to handle this? Remember this technique, because we're going to use the same technique again in heat transfer and capacitors and current electricity. So these ideas will come in total 4 different chapters. Let's see one more like this, but slightly more complex. This is a very good question. Comes in 4 different chapters. So let's say the pipe is actually dividing like this, the Y shape. Here the pressure is 3p naught. Here the pressure is p naught, and here the pressure is 2p naught. This radius of the pipe is 2a. This radius of the pipe is a, and this radius of the pipe is also a. This pipe ka length is L. This pipe ka length is also L, but this pipe ka length is 2L. There, so you have connected 3 different pipes. Let this point be A, let this point be D, this point be C, and this point be B. So A, B, C, D are 4 points there. And the pressures are 3p naught, 2p naught, and p naught. Find the pressure at D, the interface. And find out how much liquid is flowing through each cross section, each pipe. Get this, it's a pretty good question. You will see the same question in 4 chapters. In current electricity, I'll say 3v naught, 2v naught, and v naught, and I'll ask you same thing. Find the potential at point D. In heat transfer, I'll give you temperatures 3T naught, 2T naught, and T naught. The idea would be same. Everyone should give it a try. Convert them into resistors. That much I'll tell you. From there, you'll understand what to do. Convert all 3 pipes into 3 resistors. The picture will look like this. Y shape, isn't it? Start from there. Let's see. 23 P naught by 11. I don't know the answer. Could be, right? So let's convert this into resistors. So this is one resistor, this is one, and this is one. So for convenience now, what will I do? Let me call this only R is equal to 8 eta L by pi a power 4. Let's call this R. So this would be R. This was point A, this was point D, this was point C, and this was point B. What about this resistor? 8 eta L, L is double, so this guy is 2R. Here 8 eta L, L is same, but area is pi a power 4. So this guy was R by 16. Check. So the three resistors are this. Again, like I said, we are interested in the ratio. R ka value is this. 8 eta L pi a power 4. So between A and D, the distance is R. Between D and C, the distance is 2R because length is double, but area is same. D to B, length is same, but area becomes A power 4. So that is 1 by 16. This is the first thing. Next thing. Let the current from here to here be capital I. Then the current will split here I1 and I2. So this is simply conservation of charge basically. So current that is going from A to D must be equal to current going from D to C plus current going from D to B. Do you agree with this? Conservation of mass basically. Volume entering must be equal to volume leaving. Now what is current? Current is nothing but potential difference by resistance. So current in A to D is the potential difference, which is PA. Remember, current always flows from higher to lower potential. So what is A ka potential? 3P naught. C ka potential P naught and B ka potential 2P naught. So this will be 3P naught minus PD by resistance R. You're going from D to C, so you're assuming D has more potential. PD minus PC, which is P naught by 2R. D to B, so you're assuming D is greater. Now see, you can ask me, sir, how do you know current is going like this? Why can't it go that way? So don't worry about it. Science will take care of it. You assume any direction, you'll get a minus sign. The science will take care of it. So this guy will be PD minus 2P naught by R by 16. The reason why I took everything R, because that will get cancelled anyway. Then you get it pretty nice. 3P naught minus PD is equal to PD by 2 minus P naught by 2 plus 16 PD minus 32 P naught. Bring all PDs to one side and P naughts to one side. That would be 32 plus 3, 35. 35 plus half. 71 P naught by 2 is equal to PDs will be 17 plus half. 17, 34, 35. So PD will be 17 by 35 P naught. Please check. Right, Samya. Please check your calculations. Always be careful when I take the directions. Current flows from higher to lower. So if you say you're going from A to D, then A is higher than D. If you say you're going from D to C, then PD minus PC. Then PD minus PB. Please check. Once you got this, you're done basically. You want to find current in A to D, so take PD and substitute here. This is the current in DC. This is the current in DB. So you got everything there. All clear with the equations. Clear, Shaunak? Shaunak, are you there? Yeah. Utsa, clear. Shriyansh, clear. Rudransh, Anvita, clear so far. Srihari, clear. Srihari, are you there? Yeah. Sudiksha, clear. Now, yeah, there you got it there. So what do you want to find? You want to find the flow in A to D. So IAD will be 3P naught minus PD, which is 71 P naught by 35 by R. So you just keep substituting that. So IDC will be PD, which is 71 by 35 P naught minus P naught by 2R. This is also positive. IDB will be 71 by 35 P naught minus 2 P naught. I think this is also positive. So we have assumed right directions. If it is wrong, we would have got a minus sign automatically. So you don't worry about that. All clear with this. Let's see one more. There, if you see, the whole chapter has become suddenly current electricity ka chapter. There. So this is the system there. Liquid is flowing through the pipe. Hmm. So each pipe ka length is L, radius is A. All are identical pipes. So this point, the pressure is 2P naught, and this point, the pressure is P naught. Let's call this point A, this is B, this is C, this is D, this is E, and this is F. Find R equivalent. Find the volume flowing per second. And find the pressure at B, C, D, E. I know the pressure at A and F. Find the pressure at B, C, D, and D. Let's get this. Hope you can see this. This is a Wheatstone bridge. Let's see how you do this. Let's get this. Let's get this. 24. Okay. 24 आया क्या रे? हाँ, you're right. I'm just seeing everything in terms of R. So there, this is your circuit. You can replace this with a resistor. Resistor. There. There. 6, 7 pipes become 7 resistors. This is A. This is B. C, D, E, and F. And you can call the resistance R is equal to 8 eta L by pi A square. So all these are R only. You can clearly see this middle section is a Wheatstone bridge. That means pressure at C is equal to pressure at D. So you can remove the resistor between them. So CD can be removed. So basically, if you actually make a thing like this, and if you construct a house in this area, right, you will find this in that particular area, this water is stagnant actually. The water will never flow through the pipe. The water in that particular pipe will be stagnant. If you make a hole, water will come out, but that liquid in that thing will be stagnant. CDE can be removed because there's no pressure difference, liquid will not flow through it. So now your resistor circuit becomes like this. R, 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 R. Then you can clearly see this. These two are in series, that will be 2R. These two are in series, that will be 2R. 2R and 2R are in parallel. So your circuit becomes like this. R, R, and R. So the entire middle section is R. Therefore, R equivalent will be 3R. And the volume flow per second will be pressure difference. The pressure difference is P naught by 3R. That is the volume flowing per second. Arya.
So it's a silly doubt. Why is it called Wheatstone?
I think the guy who must have done this, uska naam dal diya abhi.
Okay.
There's a guy called Wheatstone. You must have figured it out. Then it is like, why didn't you ask like why it is called Poiseuille's equation?
I mean, like
There's a guy
poisonous
called
sounds like a
Poise.
name.
Uh, the Wheatstone Bridge, maybe I don't know how the name came. अभी इतना history का पीछे देखा नहीं. Search and tell me if you find something interesting. Who knows? He might be, beating the wheat with a stone and then he figured out the circuit. So could be anything. Could be anything. अभी the question हुआ नहीं. We found this thing red. We need to find the pressure at B, C, D, E. Let's get that. How do you find the pressure at B, C, D, and E? Yeah, there is a guy actually named Sir Charles Wheatstone. So there. Even though it is invented by Samuel Hunter Christie to accurately measure, Christie himself giving credit to Wheatstone for bringing it to prominence. So someone did it. Someone made it prominent. So Wheatstone basically took it. Pressures 5p by 3, 3p by 2. That looks right, Raditi. Pressures, everyone. Let's get that. We have one answer. Samyak PCPD wrong है PCPD you can actually see and guess, right? वो symmetry से midpoints है वो दोनों. You can actually feel, right? They are the midpoint. It should be 3p naught by 2. 9p by 6. Huh? That is 3p by 2. Now you can simplify it further. So how to do for this? Listen. R, R. So this is 2p naught. First of all, so how does the current flow? Now, if the current in this wire is I, we know by symmetry, up and down both are identical. The branch will be I by 2 and I by 2. This will be I by 2 and this will be I by 2. Again, current will come out to be I. So current, this is how it will split. Now, if you go between A and B, now what is I here? We calculated I value just now. How much? P naught by 3R. That's your volume flow. Perfect. So when you go from A to B, the I is equal to pressure difference PA minus PB by R. But what is I? P naught by 3R. And what is PA? 2P naught minus PB by R. RR will cancel. You end up with PB is equal to 2P naught minus P naught by 3, 5P naught by 3. See how we did this thing. We simply did current is equal to potential difference by resistance. Then let's go from B to C. B to C, current is I by 2, which is PB minus PC by R. This is P naught by 6R. PB is 5P naught by 3. This is PC by R. RR will cancel. You end up with PC is equal to 10 minus 1, 9 by this. So that will be 3P naught by 2. By symmetry, this is also equal to PD. Then go from E to F. I is equal to PE minus PF by R. This is P naught by 3R. PE minus P naught by R. So pressure at E will be 4P naught by 3. Check. We are just using the same formula. Current in a resistance must be equal to potential difference by resistance. Check. All clear with this? Any doubts on this? So yeah, that's a pretty good circuit there. Then the same thing we can use for other chapters also going ahead. You will see the same question later on. Okay, that would be the last one for the day. Next class when we catch up, we'll continue from here. Again, not much is left. Maybe we'll do one or two more problems on this, and then we'll do something called Stokes law. So next class, I think we'll finish off in the first half of the session, and then second half we'll start off with something called surface tension. Viscosity is a small chapter, but we have some pretty solid problems though. Okay, with that we'll wrap up for the day. So any doubts, anything else, please stay back and ask. Also, you're free to leave. And do remember there's a test online till Friday, and fluid mechanics is done. So do make sure to go through the notes once and do solve material on